No, no, I mean, like, maybe Andrew can introduce you and then you can start here.
Oh, Andrew, introduce. Okay.
Okay. Um, sure. Yeah, so it's our pleasure to have Yingkai here. So he's gonna talk about this constructing quantum codes from classical codes and their embeddings in ground space of local Hamiltonians. And as I understand it, it's could be like a non-stabilizer code and all that stuff. Yeah, so Yingkai did his uh undergrad in Caltech and a master's and PhD in a Waterloo, and then he did postdoc in SCTD and also in CQT, and I believe in Marco Tomamichal's group, right? Um, so, and yeah, now he's in University of Sheffield, and yeah, Yingkai, please take it away.
All right. Thank you, Andrew, for the nice introduction, and Kishore for inviting me to this talk. And today I'm very happy to share my work on constructing quantum codes from any classical codes and embedding in the ground space of local Hamiltonians. Yeah. So this talk is about my paper with Ramis Movassar. I mean, at the time that we wrote this paper, he was at IBM Quantum Research, but now um, he's at Google. All right. So about the main results. So there's two parts to the work. One is a pure coding theory type of result, and the second part is like how we can apply these new code constructions, this method of code constructions to put a code in the ground space of a two local Hamiltonian. So there are many different types of formalisms for constructing quantum error correction codes. So in essence, a quantum error correction code is just a subspace in a Hilbert space, such that it has some error correction properties. And a priori, it may seem like, okay, so how are you going to make a quantum error correction code with said error correction properties? Fortunately, there have been very nice formalisms, such as and successful formalisms, such as stabilizer formalism, the CSS codes, and further generalized to code with stabilized codes, where the idea is that you pick some classical structure with some promised properties, and from there you can construct the corresponding quantum error correction codes. So this paper follows a similar flavor, where we take a classical code as the ingredient, and as the output we get a quantum error correction code. However, our this work is different from the previous constructions in that we do not require many of the, well, it's a different construction, and we do not require as many constraints on the classical, underlying classical code. In fact, the only thing that we demand on the underlying classical code is its distance property. So the idea is that we are going to construct a quantum error correction code from a classical code. Let's imagine this code to be like a binary code. It doesn't even have to be a linear code. So it's basically, this code is just a subset of n-bit binary strings, you can imagine. And then what we're going to do is that we are going to have like a partition this set C, which is the classical code, into two sets, C0 and C1. And from C0, these strings over here, we're going to make a logical code with our quantum code. So our quantum code is going to be a superposition over the computational basis states that are labeled by these code words in the C0. And the logical one is correspondingly going to be a superposition of all of these code words in C1. And the structure that we're going to use is that these coefficients that are going to appearing here, they're not fully general. We are only going to consider the case in which these coefficients are non-negative real numbers. You may consider them to be positive numbers anyways, because if the coefficient is zero, you can just delete the code word and it's the same, right? But anyways, so these are non-negative coefficients here. And of course, for the I can make I can make any logical code word, I mean, in this way. But then the question is, do these logical code words form a code that have said quantum error correction properties? And this is what we like to discuss. And so let us revisit the fundamental quantum error correction criterion as laid out by Neil and Laflamme in their seminal paper in 1997. Written in a modern form, you can write this quantum error correction criterion in a very pleasing matrix equation form. So basically, you have this capital Pi, which is your code projector. And a code projector is basically, well, projects, it's basically this 0, 0 plus 1, 1 type of operator over here. It's a projector. I mean, well, it's a code projector. And then what we require is that for all Pauli's, multi-qubit Pauli's of sufficiently low weight, that is of weight up to d minus 1, if you have this condition that is satisfied, that is pi p pi is equals to some constant that depends only on p times pi, then we would say that the quantum error correction code that corresponds to this code projector can correct D errors. So this is the a very nice thing about the error correction criterion. A very complicated distance condition can be checked by verifying this matrix equation for all low weight multi-qubit Pauli operators. And of course, this idea can be generalized to the qubit setting by taking P to instead be a multi-qubit operation. And of course, this pi need not just be a rank 2 projector. It could also project onto a larger code space. But for the purpose of this talk, we are going to focus primarily on the simplest case of the encoding of a single logical qubit, in which case the projector is just like 0, 0 plus 1, 1. So this matrix equation is very nice, but let us expand out what this matrix equation means in a special case when the code projector is rank 2. So the off-diagonal parts of this matrix equation basically says that the 0 doesn't go to the 1 under the action of the P, which is kind of an orthogonality condition. Basically means that if you have a low weight error, it doesn't take your logical 0 to a logical 1. Makes sense. This is a nice property to have. And then you have the other property, which is the non-deformation condition, in which is the diagonal condition in this matrix equation, in which case you want the what I call the 0 sandwich to be equals to the 1 sandwich. You can I call this a sandwich because this P over here, I imagine it to be the patty, and the left side is like the bread on the left, the right is the bread on the right. So bread with patty is sandwich. So you want the 0 sandwich to be equals to the 1 sandwich. That's the non-deformation condition over here. So in a nutshell, quantum error correction criterion, it comprises of non-deformation conditions and orthogonality conditions. And the orthogonality conditions can be trivially satisfied if you pick the codes C0 and C1 to be sufficiently far apart, because remember that we demanded that the logical 0 be of this specific form, and hence, if we demand that the classical code that we use has a distance of d, then the orthogonality condition is going to be automatically satisfied, which is very nice. So this means that all that we need to do is to check the non-deformation conditions. The non-deformation conditions, well, there's only one equation here to check here. Well, it seems there's only one equation as I've written, but actually secretly there are many equations, because there are many P's that you need to check for, because you need to check for all of these low weight Pauli's, multi-qubit Pauli's. But anyways, it's just, well, not so many equations if you're not going to correct too many errors. All right, so you want to check this condition, and when would this non-deformation condition be satisfied? All right, so now let us ask, there's so many Pauli's that we may consider, like say if we have an X Pauli over here, then you may notice that from the distance condition, from the distance condition. Oh, I noticed that I'm not using my laser pointer. Yeah, so from the distance condition, if this P is an X operator, then obviously this 0 sandwich on the X operator is going to be equals to 0, and so is the 1 because of the distance condition. So it turns out that it suffices to only consider the diagonal Pauli's P. So we only consider the diagonal Pauli's P, which is much less than like all the low weight Pauli's. All right, so without loss of generality, let us consider P to be only a tensor product of our diagonal Pauli's, which is like tensor product of identity and Z operators. So what do we need to do? We need to verify that the 0 sandwich equals to the 1 sandwich, and we can expand out what the 0 sandwich is using well, the definition of the logical 0 as we have written. And because of the orthogonality, I mean, because of the choice of the distance of the classical code, the cross terms within the codes aren't going to go to each other. So this 0 sandwich can be written in a pleasing form as a linear combination of these code word sandwiches over here. And similarly, the 1 sandwich is written as a different code, as a linear combination of code sandwiches. And hence, the difference between the 0 sandwich and the 1 sandwich, which we want to be equals to 0, is going to be equals to a linear combination of code word sandwiches over here. It will just be like the A code sandwiches minus the B code sandwiches. It is important to note that in our code construction as later, we do not choose what C0 and C1 are first. The ingredient that we pick is the classical code C, and later we are going to decide which what the C0 and C1 is in a bit. So now, if we consider the qubit case, these things that we evaluate over here can be quite complicated. So namely, well, if we have a qubit setting, all these code word sandwiches, they're all going to be just real numbers because I've demanded that this A's and B's be real, so their squares is real. And also, the Pauli's only have real eigenvalues. However, if you take a qubit case, your generalized Z operator is going to have some complex eigenvalues, which is annoying, but you can always take the real and imaginary parts of it because I like everything to be real because I want to form a matrix because, well, I want to massage these non-deformation condition into a matrix equation of the form AX equals to 0. You see, in my non-deformation condition, I require the difference between sandwiches to be equals to 0. So now I want to rewrite the difference of the sandwiches as A times X, where X is basically what I want to solve, and X basically will be these squares of the coefficients that I have over here. I mean, related to the difference between the squares of the coefficients over here. But because the C's have different support, so in a nutshell, okay, so now I'm going to form a matrix A. And this matrix A has its components as the code word sandwiches. So the rows will correspond to the errors P, and the columns will correspond to the code words. So in each component of A would just be as such. And in the simplest case, we can just work on the case in which the code word sandwiches are real, right? So then we have this A matrix. Now we're going to write down this X. X is just like something that you don't know, you want to solve because it's a matrix equation, and then you solve it. And because now you are in the land of linear algebra, so A is a real matrix, and you have a well, 0 is a real number.
So Yingkai, just I'm trying to make sense of it. So you start with like some classical code, and which has like all of these code words, and you put some weight on these code words basically, and you partition it in 2 parts. So like you have this part like C0, and you have part C1. And maybe you do not care about some of them, like some of the code words you just like you just throw them, and you're
Yes.
saying that you put some weight on them, and the weights are non-negative but reals. And what you
Yeah.
are trying is that for it to be a valid code word, it need to satisfy the Neal-Laflamme conditions.
Exactly.
And then you are basically trying to write the Neal-Laflamme condition in terms of this a and b like the coefficient that you had, and
Yeah.
and you're saying that when you write it, it basically corresponds to solving system of linear equations.
Exactly.
Okay.
So I'm basically saying, in a nutshell, the non-deformation condition corresponds to solving this homogeneous system of linear equations, where so basically, but then it's like kind of inverse problem, right? So let's go just to make a linear algebra length. So now we're just solving this equation. So since A is a real matrix because you made it real, it is real. Then if there is a solution, X to this matrix equation, it must be real. In fact, I mean, if X is a solution, then it must be in the null space. You want a non-trivial solution, so that means that you want the matrix A to have a non-trivial null space, and the null space of the A is non-trivial if it has more columns than rows. That's guaranteed. Of course, if it has the same number of rows and columns, it could still have a non-trivial null space if there's some redundancy. But for sure, you will have a null space if the matrix is fat, you know, much more columns than rows. So what this means intuitively is that if you pick a classical code of enough code words, and the number of errors that you are going to correct is like fixed, then surely you will be able to construct quantum error correction code using this recipe. I haven't finished telling you the recipe. I just need one more step. So if suppose X is a solution,
But
a
why? How
non-trivial
do you?
solution.
Sorry, yeah. Sorry. How do you construct this matrix A? Like what
Uh,
is Aij element in this
yeah,
matrix? I mean, will you tell this
Aij
later?
is okay. In the qubit case, that the row the row is labeled by P and the column is labeled by C. And the matrix element is basically this code sandwich CPC without the real and imaginary for the qubit case. For the qubit case, then I have a real part of the matrix, and then I make a matrix A prime according to CPC. Then I take the real part of A prime and stack it with the imaginary part of A prime. Okay, let's focus on the qubit case. So there's no real and imaginary, right? So see this A matrix here. So then, yeah, so the P's are going down like this, and the C's are going like this. Okay, is it clear? All right, I suppose it's clear. Okay, so now when we solve this system of linear equations, now this x is a real vector, and a real vector will have components that are either like positive, negative, or zero. All right. So for all of the positive parts, or I would say just non-negative parts, I'll just collect them and those coefficients and declare them to be related to the C0 code. I mean, so I use the solution to determine what the C0 code is, namely the support of the x vector, which is the solution, the positive support of the x vector determines which C0 code words I'm going to use, and the negative parts will correspond to the C1 code words I'm going to use, which will correspond to the logical one. So the positive part will be for the logical 0, and the negative part for the logical 1. And the coefficients, well, it's very nice. I mean, so the A would just be the square root of the x, and the B would just be the square root of the minus x in the case when x is negative. All right, so you can see that, well, the A and B are, well, real, non-negative, and the distance condition, well, it just comes out I mean, the non-deformation just comes out of this system of linear equations because it is equivalent. So this is nice. This is the most important part of the talk, by the way. So happy to answer any more questions on this. All right. So in a nutshell, yes.
I can just
please.
clarify something. So the matrix A, so the columns of the matrix A are this classical code words, right?
Yeah, the classical code word sandwiches. So you need to take
Sandwiches.
this classical code word, multiply it with the error, and then, well, close it with the other part of the sandwich.
Cool. Thanks.
So you can calculate these sandwiches. I mean, I calculate them on my computer. I mean, I can calculate them by hand if I like. Anyways, they are just sandwiches. And in fact, they're super simple, right? I mean, so if this P is just like, in the cubic case, it's just like tensor product of I and Z's, right? So then you can see that this, in fact, the code word sandwiches are going to be equals to either +1, 0, or -1. So it's like some +1, 0, -1 matrix you're going to get on the A over here. Very pleasing, pretty matrix. All right. And anyways, so now let's say that you want a quantum code that can correct D errors and that the orthogonality conditions are satisfied. Well, I mean, what the orthogonality conditions are going to be satisfied for three if you just take a classical code of distance D, and that's what you're going to do. Now you need to consider the number of quantum errors you need to consider. Well, consider that, right? And remember that the only piece that you need to consider are the diagonal ones. So that's nice. So you just need to consider like just the appropriate Hamming ball of you just count the number of okay, so let me give an example. Let's say you want to correct one error, which corresponds to distance of 3. This means that you need to be able to have a P that corresponds 1, which is the identity error, which is no errors. And second, and you need to consider like the errors that introduce one Z error, of which there are n of them. And then you also need to consider the number of the double Z errors, of which there's n choose 2 of them. So it would be like 1 plus n plus n choose 2. And this is really so basically summing all the way to n choose D minus 1 in the case of qubit codes. But then if you considering like qubit code, then basically you have to, instead of summing over these binomial coefficients, you need to multiply them appropriately with with some a factor. So you will use like some quinary Hamming ball, and this factor of 2 arises because for quinary case you have real and imaginary part. So basically the error you can imagine it splits into a real part and an imaginary part. I mean, so yeah. So anyways,
so let's say Yingkai, when you solve it, so you will get all of those A and B, like those weights in, like, and I mean this this AC and BC, right? I mean this is what you will get.
yeah,
Yeah, I see.
exactly.
And
You
there
will-
will be and you will have lots of, I mean, like there will be like degenerate solutions, right?
I mean, there can be degenerate solutions depending on the dimension of your null space. So, for example, if your dimension of your null space is 1, say, then it's only one basis vector for your null space. Then, of course, you
I
can
see,
say,
I see.
oh,
Sure,
well, the
sure,
null
sure,
space
sure.
is like infinite dimensional, but then it doesn't matter. I mean, but then as far as your quantum code is considered, then that is a unique solution because your code words need to be normalized, right?
Okay.
Yeah.
So you
So
say
so
that,
so
like,
so,
I
so over
mean,
so over here,
no,
I
but
think I've done this square root thing, but I have not put the normalization condition, but because that's trivial, right? I mean,
no, but let's say even are you saying that after normalization the degeneracy is gone even if null space is
yeah.
let's say not one dimensional?
So, yeah, so if your null space is one dimensional, the degeneracy of the null space is, I mean, of the code construction is gone because you normalized it. But then if your null space is dimension 2, then you have infinite number of codes. I
Okay.
mean, you have
So
infinite solution.
which is nice, but in that case, like you could try to choose depending on some other measure among all those solutions, which solution I like more, like, I mean, like one can put some, preference, right?
Yeah, so you might, so maybe there is some other property that you require of the code that is not encompassed
Yeah.
by neural Laflamme, but
Need
maybe
love.
you have some practical application. Maybe you have some other constraint. If you can put it as if you can put it as a linear constraint in terms of this x, even better. Then it's like, wow, you can use linear programming to solve. So that's the hope, of course. Yes. Yeah. So what one of the motivations of this is that you have a very clean way to solve for the code. And then, and so basically, yeah. All right. So any questions at this point? All right. So now, because you know that if you have a non-trivial null space, you can make a code. So as long as there are more columns than rows, you can make a code. So this means that as long as you pick a code that is of distance d that's large enough, which is larger than this, the number of errors that you need to consider, then you must have that quantum code according to my recipe. And that's quite nice. And so then there's the next challenging question, like, all right, so we have encoded one logical qubit. So we have logical 0 and logical 1, but can you make like logical 2, logical 3, logical 4, and so on? Well, that's actually quite challenging because now, all right, so the idea in which we want to solve this is that we want to take an iterative approach to solve this problem. So so remember that when we solve the one logical qubit case, which is just 2 logical code words, we just pick a classical code, and then the C0 and the C1 they just fell out from the sky. I mean,
Are you speaking? Your Yingkai? I think maybe somehow you're not audible. Can others hear to Yingkai?
No, I can't hear him either.
Oh. I don't know. Is she accessing chat something? What should I do? Yeah, maybe I just do this. Yingkai.
His video is freezing. Perhaps you have like some connection problem.
Yeah. Yeah, I mean, this idea is nice. Maybe, like one can get, one can use it to build a non-uniform spherical codes.
Yeah, I'm also
So
thinking
in a
that
spherical code, like the question was that, yeah, Shubham had, like only uniform weights, right? And for non-uniform weights, it was an open question. And he also had, like on a sphere, like and he was partitioning it into 0 and 1, and then after that applying nil Laflamme, but he was connecting it with the Easton nil, sorry, the T designs. But here, instead of that, you could maybe put non-uniform weights, similar to what Yingkai is doing, and then you can get maybe, like spherical codes with non-uniform weights.
Yeah, you could perhaps also come up with this linear equation for subsystem codes there. I don't know.
Yeah. Yeah, I could just email you. Yeah. He's there.
Hi. Sorry, my computer wanted to restart.
Okay.
There was a
Yeah,
blue screen.
sometimes you need a, sometimes the computer also needs a rest, right? Yeah.
Yeah, my computer has been. Sorry about that. Just the blue screen popped up and it said that it must restart now. And I said, oh no, I'm not sure if you heard that. Yeah. So
Maybe we could start. I mean, I think we can't see you. Maybe the camera, maybe up, and I think maybe turn the screen sharing or something on. Yeah.
yeah, I'll do the screen
Share.
sharing.
Sure. Sure.
All right. Do you see the screen?
Yeah.
Yes.
Yeah. Perfect. Yeah.
Yeah, that's
Yeah. I think you were in slide 10. Yeah.
Yeah.
so just now I was talking about embedding more logical code states. So now the idea is that we are going to use a linear programming method to find how to make more logical code. So the idea is the following. So previously we had the condition that if you have the A matrix, it multiplies by the x is equals to 0, but there was like a positive part of the x vector and a negative part of the x factor over here. All right. So basically, what you would like to have is that you want to, or similarly, um, uh, have the condition that the A2, so you're making the third logical code word. So you want a similar condition for the corresponding A matrix. And the reason why, and by translating this back to the error correction man, this basically means that the first logical code word and the second logical code word, they deform equivalently under the errors. So if you want to check that the non-deformation conditions hold for code word 1, 2, and 3, then it suffices to check between the code word 2 and 3. And that's why we have this condition over here. However, because in for the first two logical code words, you've already chosen like the support. You've already chosen what the support would be. So for the A2, so you must use that part over here. And then, so in your linear program, you need to solve for x2 over here. So then x2 is the unknown that you will solve over here. So you start from something that you know over here, and you try to solve something that you don't know over here. And then you can, I mean, you're not always guaranteed to find a solution, but if the solution exists, you can always use like a particular algorithm, Dean's algorithm, to find the solution. So that's our point, is that you can use linear programming to find a solution to more logical code, for more logical code words to embed according to the code that you choose. So the idea is that you chop the code into C1 and C2. You can solve in the usual way, but then you chop your classical code into more and more pieces where you hope that you will find the code. And if you do, great. If you don't, then you just keep trying the other blocks. So there's no guarantee of success in this method, but we expect it to succeed with high probability. But what we prove in our paper is that if the code C is a random code, this procedure will succeed almost surely with high probability. And in fact, we are able to recover the quantum Gilbert-Bashimov bound in this case. All right. So this is what our next result is that if we use this procedure to encode more logical qubits, then you can derive random quantum codes with linear distance constant rate, which is another way of making random codes. I mean, there's so many ways of making.
So like,
codes.
is the weight large? I mean, if let's say if it's also like LDPC, then it solves the good LDPC question, right? I mean.
Yes, so we were motivated by the LDPC question. However, I must be said that this formalism, I mean, I'm just making codes with maybe with large distance, but then codes with large distance were already known in the pre-quantum LDPC era. I mean, they just have large maybe stabilizer weights or whatever. I mean, but over here, because we are constructing the codes devoid of the stabilizer formalism, so it's not clear what the stabilizers would be, or if they're even stabilizers to talk about. So and hence it comes the second part of our talk where we discuss like, oh, all right, so can we put this the codes that we construct in a ground space of some local Hamiltonian? So then the local Hamiltonian is in some sense like in correspondence to the low weight stabilizers in the LDPC setting. And that was our motivation, but it is not an exact correspondence. So while we were motivated by the quantum LDPC question, it is not an exact correspondence. And indeed, after our paper came out, yes.
But still, like Yingkai, but let's say, if you can get linear distance, if you can get constant rate, then that's what people were looking for, the good LDPC codes, right? I mean.
Yes, but they furthermore need the condition that the stabilizers for that are low weight stabilizers.
So here you can have like high weight stabilizers.
Yes. And in fact, if you have high weight stabilizers, it is well known even like 20 years, maybe, before that you can have high rate and high distance codes.
So how does the weight here scale? Like, I mean, how is the weight?
So for our construction, we do not know how, but if you pick like a random stabilizer code, then almost surely it saturates the Gilbert-Bashimov bound. That means high rate, high distance. And then the weight for those random constructions, we also do not know. But then you have the upper bound. I mean, so the upper bound of the generators, of the stabilizers would just be just the distance of the code. I mean, just from trivial arguments on stabilizer codes. I mean, because the stabilizer is in the normalizer, and the distance of the normalizer is at least the distance of the code. But then the distance of the normalizer is, if you pick a random code, almost surely it's going to be, So you could pick, So essentially, you're going to have, if you pick random codes, you're going to have high distance stabilizer weights that generate.
I see. And I don't know whether it relates, but there was this NLTS paper, right, where they looked at, by Anshu, Nirke, and Brookman, they looked at the low-lying energy states, and those energy states correspond to some Hamiltonian coming from good LDPC code. I don't know whether it makes sense to look at the low energy states of the Hamiltonian corresponding to your work, and show that they require some logarithmic depth circuit to prepare. I mean, maybe that can be another proof of the NLTS conjecture, right?
Yeah, but then our codes are a bit different from the quantum LDPC type codes, because in the second part, when we put the code in the ground space of Hamiltonian, we actually put it strictly within the ground space. We don't use the entire ground space, which is usually discussed when you say we have Hamiltonian of LDPC code. You use the entire ground space of that Hamiltonian is the LDPC code. However, for us, it is we're only using a tiny fraction of the ground space. So it's a bit different.
Okay. Okay.
Of course, there could be some connections, but it's not so clear at the moment. All right, so let me just skip through this part because I already mentioned about having, a random codes. This is really just, yeah. Anyways, because we have invented this machinery, so we went crazy and we just say, okay, so the theory says you can pick your favorite classical code and let's make a quantum code. So let's just, pick your favorite classical code. Oh, if you pick a repetition code, what you're gonna find? Nothing. You can't. Yes. So our algorithm. So the A matrix is has the null space is just zero. It's a dimension zero null space. So we find nothing. All right. So we put the classical 743 Hamming code. We get the Steen's code, which would nice. And then we put in like a cyclic code, and we got a CWS code. And of course, we can get beyond CWS codes because we can put in anything, right? We can put any classical code, and in fact, we can generalize beyond these idea of like superpositions of you know computational basis states. Instead of superpositions of computational basis states, you can imagine that these C's now no longer correspond to computational basis states. They're just labels on like highly entangled states. You just label them with like some bit string, right? And then yeah, so you could think about that. And if you think about that, you could have those basis states. Now, instead of being computational basis states, you could have them to be like Dickey states. And then if you have Dickey states, which are uniform superpositions of computational basis states of constant Hamming weight, then you can also design permutation invariant codes. So like you could design codes on these as superpositions on a non-product basis states. So we also designed that. And in fact, we also went crazy for our classical codes. We also put in like constant weight codes. And what you get out, you get a constant excitation quantum code. So that's really cool. Oh, but for that one, we have updated archive for that result. But we'll update it soon, maybe in a few days. All right, so then it comes to the second part of the paper where we want to discuss putting codes in Hamilton in like local Hamiltonians, the ground space of. So there are lots of nice Hamiltonians, and I would say that a LDPC Hamiltonian is not so nice. Although it's a low weight, yes, low weight terms, but then they are not two-body interactions. And in physics, the most natural interactions are two-body interactions. You're never going to get like a natural four-body interactions. You're going to have to engineer them. In fact, in Kitaev's original paper on the toric code, he started from like some honeycomb model. He started from XX from X, XX, Y, Y, and Z, Z. And he started from exchange interactions, like two-body interactions. And also, there have been papers like on compass model where they consider like Hamiltonians that are like of this two-body form, where the interactions occur according to some graph. So there's some motivation to put codes in the ground space, and the idea is that maybe if this Hamiltonian doesn't occur naturally, maybe you could engineer such Hamiltonian, and then maybe you could just engineer it in such a way that can naturally suppress the noise. So if the Hamiltonian naturally suppresses the noise, and your code furthermore lives in the ground space of the Hamiltonian, then it's super cool. It's like noise is naturally suppressed, and it also corrects like codes according to the code distance. So it's like you have like two in one. So this is the idea. I mean, this is what we discuss in the second part of our paper. So we like to discuss quantum error correction in kind of translation invariant spin chains. So like so where the interaction between nearest neighbors of the spins are equivalent. And of course, this quantum error correction and translation invariant spin chains has been studied in this very nice paper by Brundle et al. In this PRL paper. So they found approximate codes, basically, and with some amount of distance, with some amount of rate, and okay, they are able to lift. Although I wrote yes for translation invariant, later I learned that actually they can they don't necessarily need the translation invariant, but essentially the main features of their codes is that their approximate codes and the distance is quite small, and their errors, when they discuss correction of errors, they discuss correction on consecutive spins. And what we like to consider is, instead of this, we consider a particular model, which is the Motzkin spin chain, which is also what the Brundle et al. Considered in um, their construction. But then we consider a different spin chain. Well, our spin chain is motivated by the Motzkin spin chain. So this is a two local. So let us invent a two local Hamiltonian, which may or may not exist in nature. Actually, I did not know it exists in nature. But anyways, let's invent it. And then we have like some p-type terms and some q-type terms for our spin s system. And of course, if you spin s, the qubit degree of freedom is 2s plus 1. And let us consider s to be at least equals to 1. So then you are using qubits of dimension at least 3. And then we consider this Hamiltonian with these p hopping terms and q hopping terms, and with some local penalty over here, which is this local penalty can be imposed like by some magnetic field, for example. And these hopping terms basically take like the 0 symbol to the m symbol. I mean, and the q hopping terms basically essentially swaps the 0, 0 to the plus minus m states. Essentially, rigorously, um, these. So this p is a projector of this form, where this funny thing over here is actually this singlet type of state over here. And what it means is, I mean, the singlet state basically means what the symbol is trying to tell you is that the 0 hops to the m, yeah, and 0, 0 can split into plus minus m, like an m on the left and a minus m on the right. So these correspond to these local projectors correspond to local moves. So like a local like a 0m can go to an m0 and 0, 0 to this m. So it looks nice. So then you can analyze, you can, so the nice thing about this Hamiltonian is that you can then attempt to solve it exactly, like, or what I mean by solve it exactly is that you can find out exactly what the ground, the description, analytical description of the ground space. You can count like the degeneracy of the ground space. You can count the gap, and you can do things like that. And so what we found is that the ground space of this spin chain, I mean, the way we constructed it, like all product states with no zeros are, are basically in the ground space. And since we have so many ground space product states in the ground space, then we can just directly use the code construction recipe that we had in the previous in the previous part to make codes, right? Oh, but then there's also, oh, I almost lied and said, oh, you can use like all product states, but then actually, like almost all product states seem to work, but then actually but you also need an additional constraint that is no zeros occur, and there's also no m comma minus m substrings. That means you can't have any forbidden substrings. But that's fine, because in our code construction, I mean, if you forbid the substrings, you just consider codes without those substrings. And so, yeah, so we just make codes without those substrings. And then we can just count the number of such product states. And then, I mean, there are lots of them. Well, for example, if you don't want any m minus m substrings, you can, for example, pick only the computational basis states with no zeros, and then like with only the positive parts, and then you're happy. Or you can just pick like for maybe for spin one, you pick like yeah. I mean, well, there are many ways you can do this, but then basically we were able to use counting arguments. Like we could say, oh, so now you can put a really large code in this Moleskine type of spin chain. Like I mean, well, by large code, I mean a large classical code that saturates maybe the Gilbert-Bashwalk bound or some explicit codes that are obtained from the Justerson type of construction to make a code that encodes one logical qubit according to the method that we had in our previous paper. Why am I going backwards? Weird. Oh no, this is oh. All right. So now I have and hence I have this 8-qubit. We made this 8-qubit code, which looks like this, and I made this qubit code by basically sticking in like some ternary Gaussian code and just trying to chop things off. I mean, so I but eventually I got this 8-qubit code by kind of playing around, and so it satisfies the distance condition, and it has this nice property, and because it has these nice properties, it has some nice logical gates as well. For example, to do a logical X, you just need to do these simple operations over here. Yeah, and yeah, so that's it. And then we had some questions on like, all right, so what can we do with maybe our work has some implications on quantum LDPC, but as we know, the problem is already solved. I mean, because after our paper came out, they had the quantum LDPC codes of constant rate and like linear distance were constructed, so that problem was closed. Yeah, so I'm happy to take questions.
Yeah, so if someone has question, maybe please unmute yourself and ask Yingkai. So what was this? Yeah, if somebody has it, yeah. Oh, maybe not. Okay. So what was the result of this paper, the stock paper, 2019? Oh,
so the result of this stock paper is that they discussed like approximate quantum. They had this 10 local Hamiltonian, and they put this code in as the ground space of this 10 local Hamiltonian. And they found that it was an approximate quantum error correction code, and they called it a quantum LDPC code because their Hamiltonian was 10 local, which is constant in the locality.
I see.
So in contrast, we constructed our code for 2 local Hamiltonian, however, strictly within the ground space, and we satisfy the error correction conditions exactly.
I see. I see. I see. So you know, like Yingkai. So let's say, I mean, I think Andrew also maybe asked this question. So or maybe he was thinking. So when there was this, you know, video was, I mean, when you had some this trouble reconnecting. So the question is this. So let's say the Neal-Laflamme condition that you are using. I mean, people have generalized it for, you know, like more general cases, like subsystem codes and I don't know, for locate codes. I mean, dynamical codes and so on. So do you think that using more sophisticated Neal-Laflamme conditions, one can further refine your framework? I don't know. I mean, like, what do you think?
Yeah. I mean, I think that along the direction of subsystem codes, maybe is maybe not so compatible because in the first place, it doesn't have the codes do not have a stabilizer structure. So then the notion of subsystem may not make so much sense. But however, the notion of demanding additional properties on the codes could plausibly be brought in by adding additional conditions in the matrix equation type of framework. So that's a possibility. So the connection is not so clear, but there's definitely potential. Haven't thought about these problems.
Very nice. Yeah. So thanks a lot. Yeah. So I think if anybody has any question, maybe like please ask Yingkai.
Yeah.
I'm just wondering in the this linear equation, what happens if you consider just say diagonal and non-diagonal Paulis? Seems like that will only give you some imaginary terms, no?
So if you consider non-diagonal Pauli like an X operator, then these sandwiches will evaluate to 0 if they are low weight. So we don't have to worry about them. So that's why we only consider the diagonal Paulis. For qubit Paulis, you don't have to worry about the imaginary parts because they only have real eigenvalues. You only need to worry about the imaginary part if you're considering like some qubit code.
Yes. Okay. Thanks.
Okay. Any more question? Okay.